You ever seen one of those amazing AI demos, right? An AI that can perform some superhuman task, but then you change one tiny little thing in its environment and it just completely falls apart? It feels like we're so close to truly intelligent machines, but a huge piece is still missing: genuine adaptability. Today, we're diving into a fantastic paper by Kashgar Gamadi and Abulfazl Zaraki that proposes a unified way to build a much more flexible and, frankly, a much smarter kind of AI. I mean, think about it. We have these incredible robots that can assemble electronics with pinpoint precision, and we have large language models that can write poetry. But take that same robot and put it in a factory with slightly different lighting, or ask that language model a question in a totally new way, and suddenly their performance can just tank. They often can't generalize beyond what they were trained on without a ton of expensive retraining. And that's the core adaptability problem we need to solve. So here's how we're going to break it down. First, we'll unpack the two main ideas for how to teach an AI to adapt. Then, we'll look at the really clever tests the researchers set up to push these ideas to their limits. After that, we'll see if this all holds up in the real world, with a real robot. And finally, we'll bring it all together with their big idea: a unified intelligence framework. Okay, so at the absolute heart of this research are two really powerful and, you might think, competing ideas for how AI can learn. On one side, you've got inferred-structure learning, we'll call it IS, and on the other, you've got in-context learning, or ICL. Let's dig into what makes each one so different. So you can think of inferred-structure learning, or IS, as the deep, methodical student. While it's training, it isn't just memorizing stuff. No, it's actually trying to figure out the fundamental rules of its world, the hidden structure, the physics of it all. It does this by slowly optimizing its internal wiring, its parameters, to build this really deep model of how things actually work. Now, in-context learning is basically the polar opposite. It's the fast, agile adapter. This is the magic behind a lot of today's big language models. After its training is done, its core knowledge is frozen. To adapt to something new, it just looks at a few examples you give it in a prompt, that's the context, and it figures out the new pattern right there on the spot without changing its core programming. It's like getting a new play from the coach and running it perfectly, mid-game. And this table just lays out the differences perfectly. Look at the learning phase row. See? IS happens during training. ICL happens after training, when you're actually using it. And check out the key strength. IS is all about encoding that deep, causal structure by optimizing itself. ICL is all about that lightning-fast, parameter-free adaptation. They are just fundamentally different ways of tackling the same problem. So if they're so different, how do we know which one is better? Well, to figure that out, the researchers designed this brilliant set of experiments. You can think of it like an arena, where they could create very specific challenges designed to favor one approach over the other. They came up with two kinds of curveballs. The first is a structural shift. This is where the deep underlying rules of the world change a little bit. The chess analogy here is perfect. The board is the same, the rules are the same, but now the pieces are a little heavier. The physics have changed. The second is a contextual shift. Now, the physics are exactly the same, but the goal is totally different. You're not trying to checkmate the king anymore, you're trying to capture all the pawns. The game's context is brand new. And get this, the results are so cool. When you hit them with a structural shift, that change in the underlying physics, the inferred structure agent just crushes it. Its deep model of how the world works, which it built during training, lets it adapt way more effectively. The ICL agent really struggles here, because you can't learn new physics from just a few examples. But then you flip the script, you throw in a contextual shift, a totally new goal, and suddenly the in-context learning agent comes out on top. It just looks at the new instructions in its context and adapts instantly. The IS agent's deep knowledge actually gets in the way here, because it's so optimized for a goal that doesn't matter anymore. This just beautifully shows how they complement each other. Okay, this is all great in a simulation, but let's be honest. The ultimate test for any AI research is the real world, with all its messiness, noise, and just unpredictability. It was time to see if these ideas could survive a real robot. So meet the Neuro Ned 3 Pro. It's a 6-axis collaborative robotic arm, and this is where the researchers really put their theory to the test. They didn't just simulate a robot. They collected real data from this actual piece of hardware to see if the principles they found would hold up. And they didn't mess around. They collected 2,400 real-world observations straight from the arm's sensors. This is proprioceptive data, so the robot's own sense of its joint positions, where its gripper is, that kind of thing. This is data with real sensor noise and physical quirks, the stuff you can never perfectly fake in a simulation.
So what was the verdict? The theory holds up. The researchers confirmed with extremely high statistical significance that the advantage the inferred structure agent has with structural shifts works just as well with messy, real-world robot data. This is a huge, huge deal for bridging the gap between AI theory and practical robotics. So, what does this all mean? Well, experiment after experiment showed the same thing. IS and ICL aren't rivals. They don't compete, they complete each other. And this leads right to the author's biggest idea, a unified framework for what adaptive intelligence should look like.
And the work they did here is really substantial. They developed a formal Bayesian framework to describe both learning types. They ran a dozen different experiments, and of course, they validated the whole thing on a real robot. What they've really given us is a blueprint for building a completely new kind of hybrid AI.
So here it is, the big, beautiful, unified idea. We need both. A truly adaptive AI should use inferred structure learning to build a stable, long-term model of how the world works, the physics. And then it should use in-context learning as a fast, flexible layer on top of that, letting it reason and adapt to short-term changes, the rules of the game.
As the authors themselves say it best, IS and ICL are not competing alternatives, but complementary components of a unified adaptive system. This completely changes the conversation. It's not about asking which one is better anymore. The real question is, how do we get them to work together? This research gives us a powerful foundation for building the next generation of truly adaptive machines, a future where our AI has both deep, underlying wisdom and quick, nimble wit.